Quick review from yesterday. We have our energy level, which can be designated with an N. Our sublevels are going to be the shapes, which are S, P, D, and F. And we talked also about the number of orbitals that can exist within each of those. So that's just review. And then here we're just seeing that this tells us something about our energy levels. So here's our new stuff, and this is the notes that you have in front of you. You've got quantum mechanics, and this is what Schrodinger came up with, and it's a mathematical approach to figuring out where these electrons are and the properties that they exhibit. So the way this chart is set up is that we have our nucleus down here, so we're showing that we have increasing energy levels as you get further and further away from the nucleus. So a reminder, yet again from yesterday, that if we were to think about the number of sublevels, how many sublevels can you have in the first energy level? One. Which one is it? You guys remember which? An S. So you can have an S in that first energy level. How many can you have in the second energy level? 2, 3, 4, 5, etc. So just a quick reminder, this was S, this was S and P, this was SPD, this was SPD, F, and really that's as much as we did. So don't worry about knowing any of the others. Thinking about the number of orbitals in that first energy level, where you only have an S, how many orbitals can you have? Just one. Just one. So in your second energy level, where you have an S and a P, how many orbitals can you have? 4. Because you're just adding them up. And the third energy level, how many? 9. And the next, 16. What would this be? 25. So it sounds to me like you guys remember that for any energy level N, you can have N be your number of sublevels. And then what would our number of orbitals be? N squared. And then finally, the last one. How many electrons can exist per orbital? 2, so all we have to do is make this 2n squared. So that's going to be 2, 8, 18, 32, and 50. So again, hopefully that feels like review, but this is going to kind of help to sum things up. This is what we saw at the end yesterday. We were just kind of had our curiosity tweaked a little bit or peaked a little bit with the idea that our periodic table is going to tell us a lot of this and how this is set up. So we saw that, yeah, there happened to be 2 columns here in our S block, 6 in our P, 10 in our D, and 14 in our F, which is the same number of electrons that would fit into those sublevels. So this is pretty cool because it gets kind of complicated to just memorize a lot once you get into multi-electric atoms, anything that has more than one electron in it, which is most of them, everything but hydrogen. So because of that, we can use our periodic table, and it really makes it easy for us to follow along doing this. And if we were to expand our periodic table, in other words, just think about how numerically it works. You just look at the atomic number. You could see here hydrogen's number 1, then it goes to helium number 2, lithium, beryllium. So we're just going 1, 2, 3, 4. Then things get a little weird after barium right here. Depends on what periodic table you're looking at. Sometimes there's a little bit of a difference, but with barium, which is number 56, then to go to 57, you have to go down to the rare earths, or the intertransition metals, and that's when you would go 57 all the way to 71, I think it is, or 70, and then back up to 71, back up to your D block, and then moving on from there. So that's how we're going to think about this. Even though our periodic table doesn't look like this, this is what we're going to be envisioning, is we're going to go in this order. So this order happens to be known as the Aufbau order, which in German that just means building up. So I don't think you have that written on your notes. We'll get that later on a separate thing of notes, but feel free to write it if you want. But it just means building up, and it tells us the order that these electrons fill the orbitals based on energy that they have. So now this takes us to the back side, what we want to be able to do is we want to be able to write electron configuration. And there's a couple things that we can see when we write electron configuration. So here's an example. Let's think about what these numbers mean. This first one right here, what does that 1 mean? First energy level. So here it tells us it's that principal quantum number, but I kind of like to think of it in terms of energy level. So that's what it's telling you, is the energy level that that electron exists in. And then the second thing that we have shown there is a letter. It happens to be an S. The way it's phrased here is that it's the type of orbital the electrons are in. Well, or set of orbitals would maybe be a better way of phrasing that. But instead of that, let's think of it as just being the sublevel. Because for your sublevels, you've got sets of orbitals that exist there. And then finally, you have a superscript number, and we have not seen this yet, but that's going to be the total number of electrons that are in that set of orbitals, in that sublevel. So looking back at this, what is the maximum number of electrons? What's the maximum superscript you could have for an S block? 2. What about for a P block? 6, and for a D, 10, F would be 14. So that's the maximum number your superscript could be for those guys. Okay, so for this first one, and what you're going to want is a periodic table out in front of you. So for this first one, in fact, I'll give you guys a second to do that. Okay, so let's also make mention of this, that when we add up all of our superscripts, they're going to total our total number of electrons. So let's say the sum of exponents equals total number electrons that exist in that atom. So the sum of the exponents equals the total number of the electrons in that atom. Well, this first one's really easy. We'll look at our periodic table, and I'm just going to have to flip back and forth at times here. But I'm just going to hydrogen. These don't have numbers on it, but you have one in front of you that has a number on it. And everybody knows that this is just 1 is the atomic number. Now, we're assuming all of these are going to be neutral atoms. So if it has 1 proton, how many electrons? 1, right? So we're going to assume that if it's got that many positives, it's going to have that many negatives. So which energy level, I'm just going to kind of label some periods here. Which energy level does hydrogen, 1 electron in hydrogen exist at? First, right, just that 1. Hey, what block is that electron in? Sublevel is it in? The S block. So when you write this down, you're just going to say 1s, and how many electrons? Just 1. So 1s1. That would be the electron configuration for the hydrogen atom. Maybe even over here, you want to make yourself a note that's E negative, and then I put an S after that. That just means electrons. So I'm taking into account that there's 1 electron for hydrogen. I'm just making myself a note of that. First couple are pretty easy. Then we move on to helium that I see it is number 2 on my periodic table. Also notice the way this is set up, that your periodic table, typically you have helium right here. So instead, we have moved it over to the S block. It fits nicely there for a couple reasons, so let's just go ahead and accept it as being there right now. So we know that we're going to have to take into account 2 electrons. Where are those 2 electrons? What energy level? The first. What block? It's going to be that S block. So we're just going to write this, in fact it's written up above, as 1s2. So that's the electron configuration for helium, 1s2. Okay, now we're moving to a lithium, which has 3 electrons. When we go to lithium, we see that it's moved down. It's in a different period. It's not in that first energy level anymore. So I still have to take into account that 2 electrons exist in that first energy level. And in that first energy level, they happen to be in an S sublevel, that one orbital that's within that S. But where is that third energy level, where, I'm sorry, electron, where's that going to be? In the second energy level, what shape? S, and it's just one of them. So the way we're going to write this, you still have to account for the other two. It's going to be 1s2, 2s1. So all we did was just count along. When I add these up, those equal 3 for my number of electrons. Okay, I'm going to jump over to boron. Boron's over here. There's 5 electrons. So feel free to say it out loud. We're going to go all the way to number 5. So it's going to be 1s2, 2s2. And what do you think? Not 1. 2 P1. Okay? It's okay if you're confused. It'll go away eventually. So 1s2, 2s2, 2p1. Okay, so now we're going to oxygen, which is off the slide a little bit, but that's what this one is. There are 8 electrons in oxygen, which we find right over here. So to go to oxygen, everybody is going to chant along. We're going all the way to oxygen. So it starts off 1s2, 2s2, 2p4. Fabulous. Yay. So 1s2, 2s2, 2p4. We're on a roll. We're feeling good, so we're just going to keep going. Okay, so now we're going to neon. Okay, so now we're going to neon. And with neon, that is right here. So we have a fresh periodic table in front of us. Looks like our F block is not on here, but that's okay. Don't worry about this either. We'll get to that later. So all the way to neon, remind us of our period so we don't have to stop and think about that. Everybody ready? 1s2, 2s2, 2p6. So that is the maximum number of electrons that you can have in a sixth sublevel, I'm sorry, a p sublevel. So 6 is the maximum number. 1s2, 2s2, 2p6. If we were to add up all of those exponents, they equal those 10 electrons. So all of those electrons are taken care of. Okay, let's look at sodium. We find it right here. Okay, so we're throwing another little thing in here, not much, but we can do it. Ready? 1s2, 2s2, 2p6. Excellent. Okay, 1s2, 2s2, 2p6, 3s1. Because we've got 11 electrons, if I add all of these electrons up, we're wondering why this is 2p6. So if we add up all of those electrons, we see that there's 11 electrons that are taken care of. In our second energy level, in the P block of our second energy level, they're all filled. So we have to account for all 6 of those electrons. In order to go to sodium, we have to account for every single electron before that. According to Aufbau's principle, we build up and we increase in energy in that direction. Okay, so now that we're feeling pretty good, let's maybe even answer another question that we're supposed to get to later. If I look at sodium, what's the highest energy level for sodium? 3, right? Everybody sees that there's a third energy level. Hey, how many electrons are in that highest energy level? 1. What's another name for that type of electron? A valence electron. So we've got 1 valence electron. That's going to be one of those things that we think about here shortly. So just wanted to get you thinking about that we can see that from our electron configuration. Okay, well, we're going to go to phosphorus now, which is over here. So there happen to be 15 electrons in phosphorus. So everybody ready? Okay, 1s2, 2s2, 2p6, 3s2, 3p3. Yay! Okay, 1s2, 2s2, 2p6, 3s2, and then our third energy level, the p, they're not all filled, only 3 of them were. So that's our electron configuration. Okay, calcium, we're feeling good. This one will still make us feel good and smart. Then I'm going to throw you a curveball. So we're going right here to calcium. And here we go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. You got it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Hey, what's the highest energy level for calcium? 4. How many valence electrons does it have? 2. Let's look back at our notes on the front side. How many electrons can a third energy level hold? 18. Well, how many do we have represented here in calcium? Can you see that? In the third energy level, I see 8 electrons that are accounted for. Looks like we can hold more than 8 electrons, but why did it jump to the fourth energy level instead of going to more in the third energy level? And this has to do with the idea, and I'm going to have you write this down another time, but this has to do with the idea that there can never be any more than 8 valence electrons. So these guys are not valence electrons. They're in that third energy level, but the third energy level can hold more. Also, let me remind you that a few days ago, whenever we had the notes on periodic table, I had you write some information on here, and I said, this doesn't really come into play now, but it's going to be more important later, that these guys are your representative elements. Exactly. You wrote S and P, that those are going to be the guys that are responsible for the valence electrons. Valence electrons are never going to come from this drop-down block, which we called the transition metals, or what's not even on here, your intertransition metals, your rare earths. So we're always going to see that it comes from your main group or representative group, which we now know is our S and P. So here's what we need to write on the front of our notes with that tiny little periodic table that you've got. We know this is an S and this is a P. You've got that already. Now for your D block, what you need to do is write yourself a note that this is going to be, when you do electron configuration, it's going to be N-1 for your energy level. Basically, you're taking your period and subtracting 1 for your energy level. For the F block, which I don't have on this little thing, this is going to be N-2. So what we end up seeing is that the valence electrons will never come from a D or an F block. So with that said, we're feeling good. We're feeling like we can go to number 23, which is vanadium. And let me go back. And here we go. I think everybody knows what to do to calcium, but we're going to go ahead and repeat that. So we're going to go to calcium, and then we're going to go to vanadium from there and see if you can figure that out. So Mark, get set, go. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. Excellent. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Then we subtract that 1 and we get 3d, and that was 3. And do I have, no. Okay. Let's pretend just for a second, we don't need to write this down, but if we were to go to zinc, I'm going to write it down. If we were to go to zinc, what would this number be? Instead of 3, it would be what? A 10. If that were the case, how many electrons would be in that third energy level? 18. 18. So 10 plus these 6 plus these 2. There's those 18 electrons. We said the third energy level can hold 18 electrons. That would be where they are. So we just didn't do it for this one. But so that's why that chart makes sense. Okay, valence electrons, we've already touched on this. We know that these are going to be the electrons that are present in the highest occupied energy level. So for the most case, those are the guys that are furthest away from the nucleus. Why is this important? They're far away from the nucleus. They're not tucked inside, so they're going to be easily accessible for being knocked off or attracting other electrons. So they're going to be the ones that are responsible for chemical reactions. They're going to be involved in chemical reactions. So if we were to go back now to all of this stuff, and maybe the easiest thing is just write yourself a note. Valence, electrons, and we could go down and we could just list those really quickly. Hydrogen, how many valence electrons? 1. Helium. Lithium. Nope. 3. Right? Because the highest energy level is, oh my goodness, I'm sorry. You got this. Don't listen to me. 1, because your highest energy level is your second energy level. There's just 1 valence electron. Boron. How many in boron? 3, because you've got 2. Second energy level, you've got 2 plus 1, so 3 for boron. What about oxygen? 6. And neon? 8. Think it can fit any more? And its valence, any outer energy level electrons? Nope, that's it. It's full. That's why, what is it considered? A noble gas. That's why, because it's got a full outer energy level. Sodium, how many? Phosphorus? 5. Calcium? 2. Vanadium? 2. So happens to be these 2 right here in that 4th energy level. So that's what we see about valence electrons. Now, that's a lot of work. Do you really have to go through electron configuration to figure out your number of valence electrons? And the answer is no. Instead, let's just go ahead and make a little note here. Again, this is on the front side of your paper. What we see, we already saw that they're never going to be valence electrons from here, your transition metals. Instead, it's always going to come from your main group, which is your S and P. So we saw that all of the alkali metals have 1 valence electron. Alkaline earth metals, 2 valence electrons. 3, 4, 5, 6, 7, and 8. These are the happy guys because they have a full outer shell. They don't want to gain or lose. They don't want to bond with anybody. They're content the way they are. Yeah, so that's what we see as far as the relationship with the periodic table. It makes it a lot easier to just look at it that way. So now that you all have hand cramp, let's learn the shortcut method. And for this, you probably noticed that you were just repeating a lot of the configuration as you were working through this. There is a shortcut method that you are welcome to use on your homework when you have that, and quizzes and tests, unless you're told specifically not to. But the rule here is that once you have filled up a noble gas, you can use that as a shortcut to avoid having to rewrite everything. So what you would do is you would look at your most previous noble gas. So looking at a periodic table, you find bromine, number 35. What is the most previous noble gas before bromine? Argon. So instead of writing the electron configuration for argon, we know that those are core electrons. They're not involved in any sort of bonding or anything. Those are core electrons. We can just put argon in brackets, and then after that, we know it's potassium, but how would we write that? What would we start writing? 4s, 2, then 3, D10, and then finally 4p5. Perfect. So there is our shortcut method. Let's keep going with a couple of these because there's a couple tricks that we're going to see on some of these. Okay, palladium is number 46. And number 46, we're going to say our most recent noble gas is krypton. Not kryptonite, but krypton. And after krypton comes what? 4s2. Is it 4? 5s2. 5s2. 4d. And this for palladium, it's 8. Excellent. So there we go. Barium. Okay, this one's not too bad. What's our most recent noble gas? Xenon. And then it's going to be 6s2. So much easier than rewriting everything. Last one we're going to do together is our trickiest of all. Find lead on there. Lead is number 82. So most previous noble gas. Again, that's going to be xenon. And we know that after that comes 6s2. We just did that one. Now what? Really? You go into the D's? There's an F. So you have to think about the F's. What are we going to do there? Not a 6. Not a 5. It's a 4. So you have to subtract 2. So if I were to try and flip back here, unfortunately, sorry about this, but there's nothing showing there that after barium you would come down to your F block. So we would have, this is 6, then we go down to here, this becomes 4, then we come back up here and this is 5. So 6s2, keep going, F14, and then 5d, 10, and then 6p2. Okay, I think this is just a quick little, you guys, I think, got this already. Don't worry about some of these goofy little things. This depends upon what periodic table you're looking at. But you probably have a feel for this already, that if I were to say 6p2, you could probably go over here and say, okay, 6th energy level, p block, second one in, there it is. So if you look at electron configuration and just look at that last number letter sequence there, you could probably find it from the periodic table that way. And that is all we wrote.